This is 6.1 on Euler's method. It's called Euler's and not Euler's, right? So we're going to go ahead and talk about Euler's method. Euler's method is going to be using the differential equations which we saw in Calculus AB. If you remember Calculus AB, we had a dy over dx and we had some kind of equation on this side of the equal sign. We did two things with this differential equation. One of the things that we did was called the slope field. So if you remember, we created an x and y tables, and from there, depending on the run and the rise right there, we made little dash marks, so it gave us something like this. That gives us a slope field right there. And then from there, we also took the separation of variables, right? So where we separated the y's and dy's together, and then we did the x and dx's on the other side. We did the integration separately for each one of those. And if they gave us some point for the x and y, then we continued on, found what c was, substitute c back into the original equation, and then continued on and figure out what the y equals for the c is, okay? So what we're going to add on to this is called the Euler's method for Calculus BC. So what Euler's method basically means is that we're taking this curve right here, the blue original curve right here, and using Euler's method, we're going to try to figure out is what is the line segment that is closest to that curve right there. So we're going to create a table, and they're going to give us a delta x right there. And from there, we're going to find out what the x, y coordinates are. Once we find what the x and y coordinates are, you're connecting the little dots right there, and that's going to give us then the error or how close that is from the original. So obviously then the further that delta x is, then you're going to have a greater error because it's going to be more like a rigid, linear equation right there. So that's going to be far away. Where that closer that delta is right there, it's going to be probably closer or tighter to that original curve right there. Okay? So that's what we're trying to figure out for the Euler's method. Now to do the Euler's method, we're going to be given an equation similar to what we just had for the differential equation. So for AB, we did this part right here. We separated it, and then we got the x and the y's number right here. We found out what c was. We substitute c back in and found out what the equation is. So for BC now, we're going to be given more information. We're going to be given a delta x right there, and then once we get delta x, they're going to ask us to find the approximation of a y value when x is some kind of number, in this case 3. Okay? To do this, we're going to set this up as a table. So the table right here is the x and y. We're always going to start off with x and y on this part right here. You're always going to have a dy over dx. The dy over dx should always be the same equation that's given right there. All right? So then from here we have this delta x. Again, that should be given to us, so that's going to be always going to be the same number right there. We have this delta y. The delta y, the equation is dy over dx times delta x. So basically you're multiplying this answer right here with this answer right here to get this part right here. Okay? And then we have this x plus delta x. So the x comes off of the original equation right there. We're going to add it onto the delta x, which is always the same. So that's going to give us this number right here. The y plus delta y, we're going to take this y right there. We're going to add it onto the calculation of delta y. So this needs to be correct, because if that's not correct, then obviously your y number is incorrect as well. Okay? So that's how we got those numbers right there. Now again, our goal is to get to F3. So we're at 2.2 on the x right there. So we're not there yet. So we got to continue on. And using the same number, basically you bring it over here and you repeat the same process again. Okay? So again, the process is then add the two numbers together. So 2.2 plus 0.4 gives us 2.6. Again, this is the same, so that's not changing for us. Delta y times delta y over delta x times delta dy over dx times delta x. So we're going to multiply these together right there. That should give us about 0.52. Then again, x right there is found from the original x, which is 2.2. We're going to add it onto delta x right there, gives us then 2.4. We're going to take the y, which is 0.4, add it onto the calculation of delta y, which is 0.52, giving us 0.92. Again, our goal is to get to 3, so we're not there yet, so we keep on doing the same process again. So we get 2.6, we continue on, we get 2.8 at this point, and then we continue on. So with that 2.8, again, we're going to add those two numbers together, giving us 5.2208. From there, again, we're going to multiply these two numbers right there to get our delta y. And then from there, we're going to add the x's together. So 2.8 plus 0.2 gives us 3 right there. And then the y, we're going to take the 2.4208. We're going to add it to the delta y that we calculated, gives us 3.46496. So again, this right there is what we want, because they're asking us to find out what f of 3 is, which is the x number right there, and they're going to ask us what is the approximation, meaning the y number. So it's actually the y number right here. That's what we're looking for. Okay? So the direction question usually will say using the Euler's method. If not, find the linear approximation. That's what we're doing because that's what we're trying to figure out. So let me go back again, back to this Euler's curve right here. So some of the things I want to point out with Euler's curve is that when it's an underestimation when it's a concave up. So going back to calculus AB, the review of this is when we have a curve that goes upwards, this is concave up. So just think of it as the linear line that we're trying to figure out underneath it is going to be an underestimation. Okay? And then the opposite to that is going to be an overestimation when it's concave down. So that's usually the upside down parabola. And when it's an upside down parabola, normally we will find the linear equation right here above it. So that's why it's going to be then overestimation. Just remember that part. Also, there's an error that increases when the distance from the original point increases. Meaning that the delta right there, the larger that delta right there is, then obviously there's going to be more error on this. Because then the distance of that line right there, the linear line will be further away from this curve right there. So they're going to have an increase on the error. Okay? So we will do more of the table instead of the graphing for the homework. So let's go ahead and now set up the table and then do the classwork for that.